Our goal is to find a small signal equivalent for the whole differential pair. Okay. So, that is what I am getting at here. Okay. It turns out that there are some subtleties involved. So, that is why I am first finding the quiescent output voltage. Okay. So, now these two are the inputs where you apply the incremental voltage V d by 2 and minus V d by 2. In other words, between these 2 points you apply an incremental voltage of V d. Okay. The output is taken from here, right, and what I will try to do is to obtain the Norton equivalent of this thing. I can do that, right. So, if I have any circuit with some sources inside, I can find Thevenin or Norton between the output terminals. In this case, one of the output terminals is ground. When I say this, I mean between this and ground. That is of course in the incremental domain. All this Thevenin Norton work only for linear circuits. Okay. So, when I say Thevenin equivalent, I mean the Thevenin equivalent of the small signal circuit corresponding to the differential pair. So, that is what I want to do, and it turns out that the Norton equivalent is easy to find. Okay. So, how do you find the Norton equivalent circuit of anything? What is that? How do you do it? What quantities do you find? Huh? Input resistance. You have to find the short circuit current. Okay. So, first of all, I have to terminate this in an incremental short circuit, of course, without disturbing the bias point. Okay. So, that is the reason I found this voltage. So, what I will do is I will terminate this with a voltage which is VDD minus VTP minus square root I naught by Kp. Okay. Is this fine? So, how much current will be flowing here? What is that? How much current will be flowing there? Yeah, 0. Why? Voltage, yeah. So, if you did not do anything, if you did not connect anything, this voltage anyway would have been that, and you connect it that way, no current will flow. Okay. So, this will not disturb the bias point anywhere. That is my that is the idea. Okay. Now, I mean this is again in the this is 0 quiescent current. So, my operating point is still the intended one, which is where I have I naught by 2 flowing in the 2 halves of the circuit. Okay. So, that is how I would like to operate the differential pair. This is in the quiescent condition. Okay. So, now I apply these increments Vd by 2 and minus Vd by 2. Okay. What will be the incremental current flowing here? Please find this. Okay. So, I apply incremental voltages Vd by 2 and minus Vd by 2 to this, or in other words basically I apply an increment of Vd across the differential pair, find the incremental current. Okay. Now, in this case model the transistors using only GMs. Okay. If you throw in all the GDSs, the answer will not be very different, but you will just get messy expressions. Okay. So, please draw the small signal equivalent of this and find the incremental current flowing in the short circuit. That is the Norton current of this whole thing. Okay. Is this clear? What I was trying to do was to find the incremental equivalent of the whole differential pair, the Norton equivalent, and for that you have to draw the small signal picture of this, model each transistor by its GM. Now, remember what is the current flowing in each of these branches? I naught by 2. Okay. So, M1 and M2 will have identical small signal parameters, right. They have the same operating point, they are matched, and call the GM of that just GM1. Okay. So, GM of M1 and M2, it is easy to denote them both by GM1. Similarly, M3 and M4 will have the same GMs. So, denote them both by GM3. Okay. And please evaluate the small signal equivalent small signal current flowing into the short circuit. this I say is VDD. We have been using this notation for some time. This means that there is a voltage source of value VDD from there to ground. Okay. Just go back to the basics and draw the equivalent circuit M1, M2, M3, M4. Okay. And the output is terminated in something. I will call it V term, you know what it is, VDD minus VSG of M3. Now, what happens to each of these things in the incremental equivalent? What happens to this VICM? It will be 0, right? It is just a fixed bias. Okay. So, the gate of M1, then we have M1 itself. This is at VD by 2, or you can even call it V1. I think you will get exactly the same result. And the source, I don't know, let me just call it Vs. This whole thing is M1. And what will this current be? GM1 times VD by 2 minus Vs. Actually, this is very important. I see a lot of you writing the current source symbol without writing anything next to it. Okay. If you are very comfortable with circuits, these things will work. But if you are making mistakes, just be systematic. Draw every transistor, the quantity corresponding to each of the controlled current source and so on. Okay. And also there is always this tendency of somehow assuming that the source is at ground and writing GM times the gate voltage and things like that. Okay. So, just be systematic and do it, because there is no way, I mean, you imagine this is the first step. If you make this, if you make a mistake here, you cannot get the right answer. I do not see how, unless the answer happens to be 0 or something like that, and you by some other means you also get 0. Okay. And this is the equivalent of M2, and here we have minus VD by 2. So, what is this current source? What is the value of this current source? GM by 2, sorry, GM1 minus VD by 2 minus Vs. Okay. And now we have M3. The source is here, the drain is here, the gate is there. Okay. So, the controlled current source will be from drain to source. What happens to this line in the equivalent circuit? Shorted where? To ground. Okay. So, this is also ground, and the gate is shorted to the drain. Okay. So, let me just call this VD3 or something, VG3, you call it anything you want. What is the current source value? Huh? Yeah, GM3 times VD3. Then this is also going to the gate of M4. So, this is M3 and M4. Okay. What is this current source value? GM3 times VD3. And what is this connected to? What is this connected to? Ground. And what is it that we want to find? Current here. Okay. That is the Norton equivalent current IN. Okay. So, how many nodes, relevant nodes do we have in the circuit? 2. So, we have this and we have that. Okay. We have to equate this current to this current, right. What is the result of that? Huh? What do you get the value of Vs to be? 0. GM1 times Vd by 2 minus Vs plus GM1 times minus Vd by 2 minus Vs is 0. That will tell you that 2 GM times Vs is 0. Okay. So, this will be 0. Okay. So, the reason this is 0 is because we have an ideal current source here. Okay. So, incrementally this becomes an open circuit. As long as that is the case, as long as that current source is ideal, this voltage here will be the average of these two incremental voltages. Okay. So, if you have plus Vd by 2 and minus Vd by 2, you will have 0. If you had V1 and V2, you would have plus, I mean V1 minus V2 divided, sorry, V1 plus V2 divided by 2. Okay. So, that part actually makes it very easy. If the tail current source is ideal, then the tail node voltage will be the average of the input incremental voltages, and each of the currents will be basically half of the incremental voltage times GM1. Okay. So, this current, what is this current now? How much is it? GM1 times Vd by 2, and here it is, what is it? Minus GM1 Vd by 2. Okay. Now, we also have to equate this current with that current, right, isn't it? So, the current flowing this way is GM3 times Vd3. So, GM3 times Vd3 equals plus GM1 times Vd by 2 equals 0. So, this tells you that Vd3 is how much? Minus GM1 by GM3 Vd by 2. Okay. See, what is this? This is a diode connected transistor. What is the incremental resistance of the diode connected transistor? 1 by GM. Okay. So, it is like connecting a resistance 1 by GM in this branch, that is all. Okay. So, it is not any different from, if I had RL here, I would have got minus GM by 2 times RL times Vd. In this case, RL happens to be 1 by GM3. So, I will have minus GM1 by GM3 times Vd by 2, that is all. So, that part is actually quite straightforward to calculate, but again, if you are getting confused, do the systematic thing, okay, that will guarantee the correct answer. So, after you get certain level of comfort, you can do all these things without probably going through every step of the calculation, okay, but do not try to skip steps right at the beginning. So, Vd3 is some value, okay. So, what is this current now? We have found everything, right, we know this also. How much is that? Same as what? It is basically GM3 times that number, okay, GM3 times this whole thing. So, this current in this direction is minus GM1 Vd by 2, okay. Is this fine? So, what is IN? It is the negative sum of this and that. It is GM1 times Vd. Is this okay? So, actually the equivalent is very simple, the Norton equivalent current. What is GM1 times Vd? It is again like a common source amplifier, that is all. So, if you had a single transistor of transconductance GM1 and you applied an incremental gate source voltage equal to Vd, the incremental drain current would be GM1 times Vd. So, that is why I keep saying a differential pair is just a fancy common source amplifier, except that you can apply inputs differentially, I mean the inputs will be treated symmetrically and so on, otherwise it is the same. Now, we can also reason it out from here, right. I mean I did this so that you get used to the small signal stuff, you have to do that sometime. What is the quiescent current here? Quiescent current I0 by 2. What is, if you apply an increment of Vd by 2 and minus Vd by 2, what will be the total current in M1? Huh? Plus Gm Vd by 2, Gm1 Vd by 2, and this is I0 by 2 minus Gm1 Vd by 2, right. What kind of structure is M3 and M4? What is M3 and M4? Huh? M3 is not current source by any much, it is a current mirror, right. So, if you push this current into a current mirror, what will you get on the other side? Same. So, this is I0 by 2 plus Gm1 Vd by 2, okay. So, the current mirror, see the way I got the current mirror was saying, hey, I was wasting the current in M1, so I will use it to bias it, but it is not only for biasing, even the incremental current is being mirrored, otherwise the incremental current would have been wasted, right. Only half of the current would have gone to the output if I had a fixed current source here, but even the incremental current is not wasted, it is doubled back here. So, now we have I0 by 2 plus Gm1 Vd by 2, I0 by 2 minus Gm1 Vd by 2, the difference flows here and that is just Gm1 Vd, okay. Is this fine? Any questions? So, the Norton equivalent of the incremental equivalent of the differential pair, the Norton, I mean we have done half the job, we have calculated the short circuit current and that is just equal to GM1 times VD, where GM1 is the transconductance of the differential pair transistors, okay, at the operating point current of I0 by 2. Is it okay? So, the result is very simple, but the derivation has to be done correctly, so that you have some confidence in the results. Okay. So, now what else is there to be found? Huh? We have to find the output resistance. Okay. That thing is the same for Thevenin and Norton. Essentially, what we have to do is we do not have any incremental input. Okay. We null the incremental input. The operating point will remain exactly the same, and we find the resistance looking back that way. Okay.